So now we're recording. We'll see how this goes. Except now, as I go through, I'll have to yes, twice. So, okay. Actually, I'm gonna back these up a little bit. So you can see a little more of a screen. Okay. Has anyone happened to? I mean, you all here last class, but did anyone happen to watch any part of a video from last time I put on YouTube? Okay, I'm just asking because in case there's any quality issue with it, I need to know about that. Because in YouTube it's possible to do some enhancing to make that better. Well, sometimes that doesn't work so well either, but it's worth a shot. Okay, well, if anybody misses class, you'll have that. Okay, so nobody has any questions right now about the homework? Okay, so of course it's not due for a while, but just keep in mind I am going to have time for questions each time. I prefer not to spend the whole 75 minutes just lecturing, because at some point that will bore even me. Okay. Now, comment about the textbook. So I am still editing it. I plan to send it to a publisher on Monday because if I keep working on this thing for much longer, it's going to kill me. Well, both of my PhD advisors co-wrote textbooks, and one of them said that for the amount of time you spend on it, the money is absolutely not worth it. It's definitely going to be true in my case because upper level textbooks don't sell very many copies, and I think I get 15% or something. I don't know. I'm not sure if I'm going to last for the whole class because right now this is just exhausting me. But anyway, once it is finished, or at least the version that I have and I'm going to send off on Monday, then I will send all of you an update of it. And every so often, if mistakes are found, then especially if it might affect homework problems, I'll send periodic updates after that. But I'll try not to do it very often, like maybe once a week or once every 2 weeks. It depends on how many mistakes are found. Also, I am willing to give extra credit for any mistakes that are found. Finding mathematical mistakes is the most appreciated because those are the ones that would cause me the most embarrassment among my peers. But any mistake is good to know about, including grammatical or typo, anything like that. Also, if you look at the preface of a textbook, there's an acknowledgement section where I've thanked the students from these classes and from the last iteration 2 years ago for finding mistakes, and I list the students by name. And some of you are in there already from last semester. So you have a chance to get mentioned in the book if you contribute to making it better. Well, you're on there already. So
I am?
Well, because you said from 2015. Yeah.
Yes!
Yeah. Okay.
My duty is done.
Okay.
Do I get bonus points for that?
Well, you got some back then.
You didn't tell us that.
Yes, I did.
You did? You just forgot. They don't have 2015. How could I?
Yeah. So, okay. So that's something to keep in mind because every time we. Oh yeah. So yeah, because every time I go through this, I keep finding more things, and I feel like it's never going to converge. So, but again, the book I first used when I came to USM was a famous book by Burden and Fairs, and they both passed away. And I think Burden's daughter has now taken it over, and it's in its 10th edition or something like that. So nuts, especially because you can't really tell the difference between them. So, when I put on a new edition, I want it to be actually different. Okay, actually, I've just heard from the one student who is still not here. Okay. Now, okay, won't be able to make it. All right. But again, I'm not counting attendance as part of a grade this time, but still got to show up anyway. I'll admit that as a student, I wasn't the best about attendance, and I can also say confidently that I regret it because there's a part. I mean, I didn't rely heavily on whatever textbook there is. I know there are some students that don't show up and don't rely on the textbook, so I don't know what they do. To be honest, but, well, if we don't get a good grade, that's what they do. But really, you get different pieces of a picture from these things. Okay, now, moving forward with our wading into numerical linear algebra. Although right now you haven't really seen the numerical part of it yet. It isn't really any different to what you would do by hand, but we are getting to that point. So I'm going to make sure that this can be seen on the board. Okay. Now, the funny thing about Gaussian elimination is Gauss is one of the most famous prolific mathematicians of all time, and yet he had absolutely nothing to do with the invention of Gaussian elimination. Somehow his name got associated with it. There are a lot of things that he actually did that he deserved to have named after him, but this isn't one of them. I think actually back thousands of years, like from the Chinese, there was signs of using Gaussian elimination. Who knows? Maybe one day I'll have something accidentally named after me. I mean, I have invented methods. I just did not name them after myself because that sounds arrogant. And then my advisor, Gene Golub, refused to have a method named after himself. And when he passed away, then we went ahead and did it anyway. So maybe that's what will happen in my case. I don't know. Okay. Now, to recap where we've been is we're tasked with solving a system of n linear equations and n unknowns. All right, so number of elements in B is the number of equations, the number of elements in X is the number of unknowns, and all of that is n. What we know up to this point is how to solve certain easy cases, so okay. Just recap those. Make sure my recording computer is well positioned. Well, at least this is working. Now I'll see if it stays working. All right. So then we have the diagonal case where we just where A is a diagonal matrix. So all we do is just divide in each case. So not very interesting. Now the other cases are going to be of much greater use to us, where the matrix is upper triangular. And for that we use back substitution. And then we have the third case where it's just the opposite, lower triangular matrix. And for that we use forward. Substitution. And now, what I'm going to take a little time to do before going on to the general case is show you the algorithm for the upper triangular case of back substitution. And I'm going to write this in what we refer to as pseudocode. It's not code written in any particular language, but it resembles common programming languages like MATLAB. So something that would not be very difficult to translate into MATLAB. So now, since some of you have done this already for the quiz, what is, in words, the process of back substitution? What do you do? How does it start?
You start at the bottom and work your way back.
Yeah, we're starting from the last equation. Now, what I'm habitually going to do is we often refer to matrix entries using the letters I and J. So my notation convention I is often used to refer to a row, and J is often used to refer to a column. And because of what the rows and columns signify, a row corresponds to an equation, and a column corresponds to an unknown. Now, this isn't necessarily binding. I keep that in mind. But this is, again, convention that's often followed just to try to make these algorithms more understandable. So, going with what you said, starting from last equation and working your way up. So equation number n, and then n minus 1, n minus 2, and so forth, all the way back to equation 1. So for that, we're going to use a loop, a for loop. We're going to iterate. So I'm going to let I refer to my equation number, which will start out at n and count backwards all the way down to 1. So, and then I'm going to put an n down here. Thankfully for this algorithm, I don't need much space. Now, so the idea is in between these statements I've just written that indicate in what way I'm going to loop over all the equations, I'm going to solve for one unknown. Now, I could have used that same structure over here in any order. I can say, in fact, forget this, I can just say for I equals 1 to n, xi is bi over aii, and then n. And this, this translates pretty directly into MATLAB syntax. The only difference is, I would say, like for I equals 1 colon n, because in MATLAB a colon operator is used to specify a range of values going forwards. If I want to express this, counting backwards from n to 1 in MATLAB, that would be n colon minus 1 colon 1. And that's something that's featured in the tutorial. So, so that's how you conveniently express something like that. Okay. Now, the process of solving for a single unknown when it's back substitution is actually a generalization of what we have in a diagonal case, in that you start by setting it equal to the right-hand side value, and you're going to end by dividing by a diagonal entry. It's just that with a back substitution case, unlike a diagonal case, we have things to do in between. But I want to see the connection between the two, which is actually why I'm covering both of these, even though this seems kind of trivial and silly, but not quite. Okay, now, if you recall from last time, and maybe you might want to look at your notes for that, what happens with back substitution? You have a whole bunch of terms on the left side. You have a single value on the right side. You have to take terms on the left side and move them to the other side, and then divide. So that's what happens over here. So, so now we're going to have another loop, and I'm going to loop over columns. maybe I should give myself more room. Okay. So now, if I'm in row I, which columns am I going to loop over? Columns to the right of a diagonal. So, because an upper triangular matrix, the only non-zero entries are entries ij, where I is less than or equal to j. So in other words, j, remember, j is referring to columns. So j is going to start at column I plus 1 and keep going all the way to the last column. So it's those terms in the equation that we need to deal with. And if you refer to like an examples from last time, that's, oh, what happened here? Oh.
Oh, great.
Hopefully it's still recording while it's doing. Okay, it is. All right. So I'll have to check that every so often, or maybe.
Well, can we make it so it doesn't go to sleep?
Go ahead and do that.
Even if it's asleep, it's still recording, because I had to use that for
Yeah.
this class,
Okay.
and it would, like, the screen would go black, but it would still be recording what's going on.
Maybe every so often you can like touch the mouse
Shake the
pad or
mouse.
something. Yeah.
I can do that.
Okay. All right. So moving terms to the other side, what you can do is you can say xi is equal to itself, and we're going to subtract off one term each time through. And that's going to be an entry of a matrix, aij times xj. Now, j is greater than I. That means it's an unknown we've already computed. So, and we call it back substitution for a reason, because we're going backwards through the equations, and we're substituting previously computed values from our unknowns into equations that are above it. That's what is happening here. So, okay. So that's the whole back substitution algorithm. That's also, so this is algorithm 3.1.3. So what would be a good exercise for you to help yourself understand this is if you look at an example like from last time or earlier in the chapter and see how going through this process step by step actually mimics what you've seen like on the board last time or in the notes, worked out for an example, so you can see why this algorithm really is the correct one. And I'm highlighting this because we're about to look at an algorithm for Gaussian elimination, which works in a similar manner. It's just going to be more involved. So if you're writing a function for back substitution, it's going to follow something like this. In fact, I've pretty much written it out for you, except for differences in MATLAB syntax. So for instance, x would be an element of a vector. So yes, we are getting to vectors pretty soon. And so xi in MATLAB is x parentheses I. So you use parentheses and put your index in parentheses to refer to an element of a vector. Whereas for a matrix, aij in MATLAB would be expressed as a, and then you put two indices separated by a comma. So these would be how you would change to MATLAB syntax to express all these quantities. Okay, and since one of the homework problems, I believe, is actually to write this function. Okay, actually, yeah, problem. So this is exploration 3.1.5 is to write a MATLAB function that does this. Okay. So once you get to that point, we'll see how that goes for you. Okay. All right. So any questions about what I've written here? Because what we're doing is formalizing what you already know how to do by hand, working out these kinds of systems. That intuitively you understand what it means to substitute into equation, move terms to the other side, and so forth. But now you're telling a computer to do all these same things, and that's what, and this is how you do it. Okay. So last time in this discussion here was about how we solve simple systems of equations. But now, if we solve this kind of system where A could be any invertible matrix at all, we need to be able to reduce this general case to an easy case such as this one. And upper triangular is the one that we're going to reduce to. That's what you did in your first linear algebra course, reducing to row echelon form, which is a term that I'm only going to use to derisively refer to those kind of classes. So what we're going to do is, from those kind of classes, you perform row operations to reduce a general system like this to one on which you could use back substitution. But now, again, we have to derive an algorithm for doing that. I'm not really going to comment about forward substitution just yet. It's almost identical to back substitution. It just goes through the equations from first to last. Performs similar operations here. We will need it later, but not just yet. Okay, so now it is laptop moving time.
I'll remove this one.
Okay.
This is my
All right. I'm not sure how much of a. Almost seems like you can't see very much of a board. I don't know. Because I could see like. Oh, okay. That seems better. Okay. Well, what I'm going to do, I'm going to draw lines here to indicate my boundary. Okay. Okay. Wait, I can. Wait.
I suppose which computer are you working from?
Well, the thing is, if I'm trying to make sure that you can see.
Do you want me to scoot this back?
Actually, yeah, that'd be a good idea.
Is that better?
Okay. Yep. All right. So. Pull back.
For me, you can keep going.
Oh. Okay.
Stop.
Okay. Oh, well, that's the same view as on the separate computer. So. Okay. And then the other
And
way.
that line is like right
Okay,
out
and
of
then
view
I
at
can
the
go.
bottom half,
I can go
so-
to the end of the board.
I can't see you anymore. There.
Okay. All right, I can work with this, as long as those laptops do not move at all. Oh, actually, I do need to move this one a little bit. Okay. All right. So maybe I should spend the rest of the class here. After all the work that it took. Although, I actually want to make sure this one. Is this still actually recording?
Is the green
Yes, it is.
dot
What?
is the green dot on the camera, if it's still on,
Oh, yeah, yeah.
then it's recording.
Okay.
So,
I haven't been a Mac person for very long, so that's good to know these things. All right. Now,
is number 3 kind of the same way as number
What?
2?
oh, I was just talking about that. Yeah, and we won't need it until later.
Okay.
All right, so to reduce a general system to upper triangular form. Okay, so we use row operations Now, in your first linear algebra course, you learned about 3 different kinds of row operations. There's multiplying a row by a scaling factor. We're not going to need that one. There's interchanging 2 rows. We will need that, but not yet. So we're just going to focus on, by far, the most useful operation. So subtracting a multiple of row j from row I, where I is greater than j. And the purpose of that is to wipe out entry ij. And because I is greater than j, we're only going to try to wipe out those entries. Those are all the entries in the lower triangle. So those will be 0. What's left is going to be an upper triangular matrix. Now, it turned out that I have an example of this in the book, in this section, and I've decided, after even it's been there for literally years, and for some reason today I decided I don't like it. Maybe it's because I'm teaching this particular topic today. The reason why is it works out too nicely. I made sure that all the entries of the matrix, every step of the way, are integers, and which is harder to do than you think. But then it doesn't really translate well to. It doesn't make it easier to see how the overall process, how the algorithm works out. So I need to make the numbers less nice. So before class, I made up an example in MATLAB with, there's still reasonable numbers like fractions. Okay.
Is row supposed to say row, or is it supposed to be a multiple of column j from row I?
No, it's row.
Okay.
Yeah, these are row operations.
Okay.
Yeah. Okay. Okay, so I'm going to let A be matrix. We'll start out with integers, but they won't stay integers. 2, 3, 1, 5. Okay. 5, 3, 4, 5. And I used a function in MATLAB, rand_i, which generates random integers between a certain range. So I just want random integers from 1 to 5. 5, 1, 1, 1. And as you can see, MATLAB is not very imaginative in its selection of numbers, but it still ends up being a good example. Okay, and then same thing for the right-hand side values. B, again, MATLAB not very imaginative. 4, 3, 3, 4. Okay. Now, I've actually had MATLAB carry out all the row operations just because I don't trust myself to do it correctly here on the board. So what we need to do is to reduce to upper triangular form. These are the entries below the main diagonal that we need to make 0. So we need to, so by performing row operations, 0 of those entries will get this upper triangular form. And as we perform row operations on A, we will also perform them on B. So we work on the augmented matrix, which I'll call A tilde, which is A and with B added on as an extra column. So this is actually going to be a matrix with 4 rows, 5 columns. One, 3, 3, 2, 2, 4, 3, 3, 4. Okay. And what we're going to do is we're going to go column by column. So I'm going to use J to count columns. It's going to start with column 1, column 2, column 3. And we only need to go through 3 columns. It's all the columns of A except for the last one. So in MATLAB, it would be a statement like this. For J equals 1 up to n minus 1 for general n by n matrix. So this is how we describe how we're going to iterate over all the columns. Okay. So now we're focusing on a single column. So what I need to do is, for column 1, the idea is that we're going to let row 2 equal to itself minus some multiplier, which I'll call m temporarily, times row 1. And the purpose of that is to zero the 2, 1 entry. So remember, first index is counting rows, second index is counting columns. Right now we're only in column 1. And I'm going to name this multiplier, and I'm not going to call it the generic m, I'm going to call it m21, because it's indicating which entry we're zeroing. Okay. And we'll figure out what multiple that is in a moment. And then the process will continue. So we're going to zero out, we're going to take a multiple of row 1 again, multiply it by something, and subtract that from row 3 to zero the 3, 1 entry. So we're Xing out this one so far. And then we'll do it one more time to get this one out of the picture. And yes, this is getting repetitive, but it's kind of the idea. Because what I want you to see is a pattern. Okay. So what we're doing in each column is, I'll start writing the overall algorithm here. We're in column 1, and we're starting at row 2, row 3, row 4. So in other words, we need another iteration inside this one. And I'm going to use I to refer to rows, like I mentioned before. Now, in column 1, we worked on rows 2, 3, and 4. Now, then we would go to column 2. Where's my row going to start?
3.
Row 3. I'm not going to X out this one. I'm going to X out these two. So, and then I go to column 3 and work on what rows? 4. Only row 4. So, if I'm in column J and I want to iterate over a correct set of rows, where do I start in terms of J?
J plus 1.
J plus 1. All right. And I keep going and stop when?
It
N. Why N?
And minus 1.
Well, it's actually N.
Because they're the same.
You
If you're
yeah.
you stop it in, there is no.
Yes. You stop at the bottom. Yeah. So, yeah, once I'm in a certain column, I start at this row, like row I plus 1, or I plus 1 for this case, or sorry, J plus 1, and I keep going until there are no more rows. All right, so I'll keep going. So I is going to count from J plus 1 all the way down to N. So rows 2 through 4 in this case, and then in column 2, just rows 3 and 4, and so on. Okay. Now, and actually I'm deliberately leaving a little space in between here. So now, inside here, I'm going to perform one row operation. And the purpose of that row operation is to zero the ij entry. Now, what I need to do, although it looks like I'm not going to have enough room here, but I'll deal with that later. I need to know I know I'm going to subtract a multiple of row j from row I. So I'll just write this in here in not even pseudocode. So, but in words, I'm going to do row I is equal to itself minus the multiplier times row j. So however we're going to do that has to go in here. This will handle the matrix A, but also, actually, I don't want space there. I need to do this in A and B, so the whole augmented matrix. So I can take this whole row, multiply it by something, subtract it from rows down below, all the way to the end. So, because you're updating both sides of the equation, so you're affecting a matrix A. A determines what row operations you perform, but you have to update B also. Okay, so the algorithm is taking shape. We have this iterative structure, these two nested loops. We just have to work out the details of, okay, now we know we're going to do this row operation. What is it, and how do we implement that? Okay, any questions up to this point, though? Okay. Unfortunately, we have a moving operation again. Yes?
Oh, one question. We're continuing to reference the multiplier. Doesn't the multiplier need to go in before we define?
Oh, it will be defined in its space. Yes.
Yeah.
Okay.
Yeah,
That's coming.
So are you doing them one at a time? Or are you doing the whole row at a time?
Well, when you say one entry at a time?
Yeah, or no, are you doing like just the three? You're knocking out just the three, and then you're going to knock the rest of the row out?
Oh,
or you're not worrying about the rest of the row?
Okay, so yeah, each row operation will only knock out one entry.
Okay.
So row op, row op, row op.
But it doesn't alter the other numbers?
It will.
Okay.
Yeah.
That's what
But then once we get to the next column, we're working with whatever's there.
Okay.
Yeah.
All right. But that's an important point, actually, that you bring that up, because it means because these row operations have to work on whatever's there after these have done their job, that means you cannot do these things in parallel. It has to be sequential. Okay. But yeah, because computers these days are so much more powerful and have multiprocessors. Mm-hmm. So if you determine that there are certain operations that will not step on each other's toes, then yeah, you want to do those in parallel. And we'll see some methods this semester where that can be done. This is not one of them. Okay, so we need to focus on, now that we to the point of eliminating specific entry ij, what does that entail? Okay. Actually, what I'll do is for the next update of a book, the example I've worked on in MATLAB, like this one, I will put in there like all the steps. Okay, let's see how this goes. Okay, and once again, I'm unsure as to what part you can see, but okay. All right. Now, actually, what I'll do is I'll put up MATLAB here and show at least a first row operation. All right, so the matrix. All right. So 2, 5, 5, 3, 4. And then 3, 3, 1, 3, 3.
1 4 1 2 3
Okay, thank you.
5 5 1 2 4.
Okay. So A21, which is equal to 3. With this kind of row operation, row 2 is equal to itself minus a multiplier we have to determine times row 1. So what that would mean is we have to do the whole row. So I'm going to use another index. I've used I and j already. So if I'm going to do another iteration within those two, I need to pick a new variable. I'll use k. So k is going to go from 1 to up to n. So k is a column index, just like j is. And we're going to work on row I, where in this case I is equal to 2. So A, I, K, so an element of row I, so I is equal to 2 in this example, is equal to itself minus the multiplier, which would be Mij, because also keep in mind j is equal to 1 in this example, times the same element of row j, a j k, because we're going over all the elements, like from 1 to n. I'll handle this column later because that's b. And what I'm doing is I'm subtracting from each element the corresponding element of row j times the multiplier. Okay. And then I can do the same thing in for b. bi is equal to itself minus the same multiplier times the element from row j, which is bj. Right. So all of this is one row operation. And that is something I'm going to eventually insert into, like I have marked in the algorithm over there, a partial one, where a row operation goes. So this is going to be shoved in there. I'll write out the whole thing when I get to that point. So the whole process has been laid out except for the most crucial detail of all. What's the multiplier? We're actually going to solve for it because this entry right here is supposed to go to 0 once we do this update. So if I take this key step right here and consider the case of column, actually, I'm not going to go from 1 to n, but column j to n. For instance, when I'm over here eliminating this element, I'm not going to bother with this one because it's already 0. I'm going to do everything to the right. So k will go from j plus 1. N. I could go from 1 to n, but I'm wasting my time because I'd be manipulating entries over here that are all 0. Why do that? So, all right. So, it's very important to not perform any wasted operations. Okay. Now, all right. So for column j, all I'm going to do is I'm going to set k equal to j in here. So I'm going to replicate the same step, Aij. So wherever you see K, make it J. Minus Mij, Ajj. But Aij is the entry I'm trying to zero out. So that's supposed to be 0. So with this in mind, what is Mij equal to? You could just algebraically solve for it. Yeah, because I can move this to the other side and then divide by Ajj. So Aij over Ajj. You see where that comes from? Okay. So Ajj better not be 0. We'll deal with that later. As in not today. All right, so now we have our multiplier. But now, if we go back here, turns out I've exposed another inefficiency. Because if I'm doing this row operation for all columns starting from J all the way to the end, so taking multiple of whatever row J and subtracting from row I, when K is equal to J, what's the result supposed to be? As I just discussed. 0. So why am I actually carrying it out if I know what it's supposed to be? I could just stick a 0 there. So I'm not going to start at column J. I'm going to start at column J plus 1 and go all the way to the end. Again, we're not performing a single operation that we don't need. All those are important. So that's how we do one row operation. So to illustrate this, okay. Let's see, maybe I should do this. Okay.
You need a table with the wheels and slide it down.
I know,
Little
yeah.
cart, little rolly cart.
Yes, but we're a poor department.
Yeah, that's why there's holes in the wall.
Yeah. And also why we are literally rationing chalk. I'm not
you can get
joking.
charged for like 10 cents at Dirt Cheap.
Oh, well, apparently the university doesn't know that.
Yeah, they ain't frugal.
Oh, what?
I have a question.
Yeah.
Can you repeat what the purpose of each for loop is? I was expecting 2, and then when we got the third for loop in there.
Okay, so
Felt like I
you were
missed
okay
one
with the
for
first
three.
2 for loops? All right. So the outermost for loop, it goes through all the columns. From left to, yeah. The next inner for loop is to handle eliminating one entry within that column. But in other words, inside that second loop, we're going to do one row operation. But a row operation requires handling several elements within that row. That's why we need the third loop.
Okay, thanks.
Okay, all right. Okay, now, I guess my view here, my window's a little backwards, but I can't really tell what I'm, okay. Like on my screen, I can't see the divider between the boards. Oh, there it is, okay. All right. So what I'm gonna do is, all right.
Did we move that here?
Let's see. Actually, I'm going to take the whole table. It's not on wheels. Okay. So I'm actually going to do something that's going to really throw me off and cross halves of the board. Okay. All right. So, so the whole algorithm, we have pieces on it on different boards, but now I'm going to put it all together. All right. Actually, can you see everything between here and here? Okay. All right. So we loop over all the columns except the last one. Then within that, we loop over all rows starting right below that diagonal entry and going all the way to the bottom. So within this gap, we do a row operation. Now we need the multiplier to do the row operation. So Mij is Aij over Ajj. Now we carry out the row operation. First on the matrix, and only on columns to the right of where we are, because in the column we're in, we know it's going to be 0. So we carry out that main step that I wrote down earlier. And then we update B also. Now this is algorithm in the book 316. All right, so it's just reproduced here. So that will reduce the augmented matrix to upper triangular form. And this would translate pretty much directly into a MATLAB file that would carry this out on a given matrix A and given vector B for the system AX equals B. So this takes elements in row J, see the row index J here, multiplying them by the right factor to eliminate Aij, subtracting them from the corresponding elements in row I, and so that's your row operation. And then for B, same thing. Notice all the row indices in this step are exactly the same as in this step, because it's doing the same row operation. It's just that because B is a vector, you don't need a column index at all. Okay. So this describes systematically what you did on paper in your first linear algebra course, except for any row interchanges because we haven't got to that point yet. All right. So now if I were to illustrate that process on this matrix right here, and so now I really will have to move these things. Okay, actually, now whoever's watching will get a better view of the algorithm that now is on the left of the screen. Okay, 12 minutes, I can do this. But one thing, since we have a schedule for the whole semester, like up on the side or what I handed out first day, so you can see exactly what section or even subsection I am covering. It's a good idea to, bless you, at least take a look at that, preferably before class if you can, so you can better follow what's going on during class. Because if I'm killing myself to write this textbook, you're dang well going to read it. Well, that's also why we have the quizzes. Because if you do the reading, then the quiz should be manageable. Okay. Oh, no, I was not supposed to do that. Oh, that's okay. I still have the augmented matrix, so let's work with that. Okay. All right. All right. So for to zero out 821, this 3 right here. So M21 is equal to the element I want to get rid of, divided by the diagonal entry in the same column. So it'd be 3/2. So now I would say that row 2 equals itself minus 3/2 times row 1. So if you went ahead and carried out that operation, then that whole row, that second row, is going to be affected. And I previously worked that out in MATLAB. So row 2 becomes, so the first entry is 0, as intended. But then the numbers are not so nice after that. We get minus 9/2, minus 13/2, minus 3/2, and then for B, it's minus 3. Okay. Okay. So that whole row is affected. And then for a free one, our multiplier is, we want to eliminate this element to 1. So it's 1/2. Again, we're dividing by the diagonal element in the same column. So this 1/1 entry here. So then row 3 is equal to itself minus 1/2 times row 1. So once we carry that out, we're going to have row 3 becomes 0, and then we have 3/2, minus 3/2, and 1/2. So you can try these out. Well, I'll write this up later. You can confirm that. And then the entry for B is equal to 1. And then finally, for A41, the multiplier is, we want to get rid of 5, and we divide by 2, so the multiplier is 5/2. So the row that we get is going to be 0, and then we have minus 15/2, minus 23/2, and minus 11/2, and then minus 6. So now what happens is, these last 3 rows of the augmented matrix now become these 3. The rest of that column below the diagonal is now zeroed out. And then what will happen is we move on to the second column, and these entries are the ones that are going to be targeted. And we're going to take a multiple of this row and subtract it from each of these. Now, so can anyone tell me, as we move to the second column, I need to eliminate this entry in row 3, column 2.
Yes.
Now, what's the multiplier going to be? What?
Not negative 9/2.
What did you say?
5/4.
Uh,
Because you're using
okay.
that one and the one above it.
4/5. 4/3.
Okay. No, none of these are right.
Negative 1/3.
What?
Negative 1/3.
Negative 1/3. Why? Because it's the element you're eliminating, 3/2, divided by the diagonal entry in the same column,
which
this
is
one.
negative.
So we get minus 1/3. Okay. Now, the similar thing is going to happen with zeroing out that entry, M42. So can anyone tell me what the multiplier, okay, someone besides David, what the multiplier will be in that case?
Maybe negative 15/2 or something.
Yeah, the diagonal entry in the same column. Like
13, 9/2? Negative 9/2.
Yeah, because we use, whatever we have here, denominator,
Yeah.
we use that for that whole
Yeah.
column.
Yeah.
Yeah. So minus 15 halves over minus 9 halves is 5/3. So that will be the multiplier in that case. Both entries we zeroed out. These will be modified, and then we would need to use a multiplier based on B. This entry is the last one that will go. It won't be minus 23 halves. So those values right there are useless to us. But once they're updated, then we'll perform that one last row operation, and that'll be the end of it. So, yeah, so it's always entry you're eliminating divided by diagonal entry in same column. In retrospect, what I should have done was this. Oh my God, shut up. Is updated the augmented matrix, so you can see like, okay, this is our new second row, third row, fourth row. But, okay. But do we see now where these come from?
Yeah.
Of course, really good at a computer doing all this work. You're not going to do any of this on paper. I'm not going to give you a final exam problem to carry out Gaussian elimination. I don't think. Well, something related. But so when I took this kind of class, we had to carry out this process of it's actually called the LU decomposition, which we'll see on Thursday, to solve the system linear equations. And I got through the end, and I'm talking to a classmate afterwards about that problem, and the answer I got, and he said, well, the answer is just 101. I didn't get that. And like, so I stewed all weekend thinking, oh God, I did poorly in this test, and how many points did it take off, and so forth. And so we get the test back the following Monday, and turned out they just took off a couple points, and I got 96, and did better than the other guy. And so that's why I never ever would talk about a test to someone after the test, because that takes away hopes. Yeah. But I know students feel differently about that sort of thing. Like, what did you get for this? I'm like, no. Okay. Well, we're just about out of time, but actually this is now. We'll see. During the last few minutes that I have here. Well, actually, yeah, there really is only one other point I wanted to make. If we look back at the algorithm that I have here. Okay. And, okay, yes, it's tilted intentionally because of, as long as you can see this. Okay. So this algorithm, we have 3 levels of loops. This one carries out n-1 iterations. This can carry out as many as n-1 iterations, and this one as well. So, so the complexity of this algorithm is order n cubed. Okay, I think I just gave away the answer to a homework problem, but still, it's a very important point nonetheless. So forward and back. So solving a diagonal system takes only n arithmetic operations.
Yeah.
Forward or back substitution, we're talking order n squared operations, or well, depending on the matrix, it's actually exactly n squared. But here, a whole new level of complexity, n cubed, which is pretty bad. But a lot of methods from numerical and algebra that work on an entire matrix require that amount of effort. For instance, multiplying 2 matrices takes order n cubed operations. So we try to avoid doing these when we can. Yeah. Now, the thing is, another thing you could do to solve AX is equal to B is you get A inverse, which you learned to do in your first linear algebra class, doing all these crazy row operations to get identity. You start with identity on the right side, and then you get on the left side, and spend weeks doing that, and for what? Because it's actually pretty much a mortal sin to do that in the numerical world. And then you multiply a matrix vector multiplication, A inverse B. Now this whole process to do all of that is also order n cubed operations. So it seems like there's definitely a gain. But the thing is, it's not just the power of n that matters. There's a constant in front of this n cubed term, which we're not talking about right now. The number of operations for this process is actually 4 times as many as this one. The constant in front of the n cubed is 4 times that constant. So that's just one reason why we say we never, ever, 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 ever explicitly compute the inverse of a matrix. Well, okay. We'll see an exception at some point, of course, but it is, again, something that's highly discouraged. Okay, so, all right, so that's the Gaussian elimination process and how we have an algorithm for it now based on the process you've done before by hand. So what I'll cover on Thursday is how we make it more practical for a computer to carry out, especially for many systems at a time, and that leads to matrix decomposition or factorization. So that's where we start actually finally deviating from what you've seen in a regular linear algebra class. Okay, so, well, recording went smoothly anyway, and so did Skyping. So go figure. All right, later.